All right, thank you, everybody. Here we're going to have our last talk of the day. So we're going to have Leo, who is a postdoc at the University of Idaho, I think, right? Tell us about his work on GRHayL. So yeah, go ahead. You can flip it on or hold it.
Yeah, I'll flip it on. Yeah. Let's see. All right. Can you guys hear me online? Can you guys hear me online?
Yes.
The people at Zoom. Okay, cool. All right. So, hi everyone. I'm Leo. I realized that I'm the last hurdle between now and going back to the hotel before it starts raining out there. So I probably will not talk for 1 hour. But yeah, so I wanted to talk to you about GRHayL, a new, relatively new hydrodynamics library that we have developed, and what it is, what you can use it for, and what we plan to do it, and what we're doing with it, and what we plan to do with it in the future. So I'm going to build a lot of my talk on the talks that happened today and yesterday. So I'm going to spare you some of the details because they were already covered. So I'm going to just go a little bit faster. But yeah, so the GW170817, and its electromagnetic counterparts basically open a new frontier for multi-messenger observations. And both current and future observations, as pointed by Deidre and others, can promise further insights into these systems. And in particular, there are still several unanswered questions about them that we want to address, right? So what is the equation of state of extreme nuclear matter? And how do, for example, how do dynamical ejecta, produce kilonova? We know that they do, but how can we understand all the details about that? And also, how can we explain the abundances of elements produced by our processes in our universe? So we do that, through our simulations, and most of the simulations that my group has performed has used the Einstein toolkit. And these simulations, basically they serve as our laboratories for studying these systems, right? There's no other, this is how we do it. So we can view ourselves as experimentalists for doing these things in many ways, right? And a lot of work has been done. There's been a lot of progress. There are a couple of review articles there that I just put there for people who are interested in reading about the history and the details. And then a few of my contributions as well, and from my group as well, from, mostly on the development of new codes and that allow us to do this. And one upcoming that I didn't put there, the one upcoming one is the GRHayL publication, which is under, we're writing it right now. So I'm going to give you probably the quickest and most brief overview of how we do binary neutron star simulations, right? And the idea is we solve these equations coupled with the equations of general relativistic hydrodynamics, magnetohydrodynamics. But basically the idea, right, is that we are solving this left-hand side for the space-time, and then mu nu, the energy momentum tensor, basically, is just the matter, so it's through GRMHD, and there's communication between the two, right? The space-time evolves and influences how matter will evolve, and then as matter evolves, it influences how the space-time will evolve, and it's this back and forth that we have to deal with. And because Jay has given a great overview of this on the GRMHD part, and other folks have given a great overview on the space-time part, I'm not going to show you any equations other than this one. Right? This is the 10,000 foot overview of this thing. And so our starting point for all of this has been Illinois GRMHD. You might already know what Illinois GRMHD is, but if you don't, so Illinois GRMHD is a code inside the Einstein toolkit. It is a GRMHD code inside the Einstein toolkit. It's a rewrite of the original GRMHD code by the folks at Illinois. It was rewritten by Zach here in the room. And it's a leaner and faster code, but that agrees to the original one to round off error. And it provides GRMHD for fully dynamical spacetimes, fully open source, part of the Einstein toolkit, and it has been field tested for many systems, right? And that includes neutron stars and black holes with accretion disk, and mixed binaries of black holes, neutron stars, and white dwarfs, and pretty much everything you can think of. I think Illinois GRMHD has already been used for at some point. So this is our starting point in developing GRHayL. We wanted to brings this robustness that is associated with Illinois GRMHD and this the idea of how you know the reputation from this code into something that is don't get me wrong, like I understand that it's part of the Einstein toolkit, but you know, if we could have that in other infrastructures, that would be awesome, right? So that was yeah. So again, it comes with this idea that like because it is part of the Einstein toolkit, it is part of this monolithic code base, right? And in particular, if you are new to the game, right? If you haven't worked with the code or with the Einstein toolkit at least for a long time, and it can be very difficult to debug. It can be very difficult to extend. It can be very difficult to figure out where Illinois GRMHD ends and the Einstein toolkit begins and vice versa, right? The Illinois GRMHD has a lot of knowledge of the Einstein toolkit and it exploits that in ways that, you know, if you're new, it might be difficult to follow, right? And on top of that, it's not really future-proof. The way that we're doing things, some of the extensions were not following best practices and they're not the best way. We wanted to make something that is a little bit better for everyone. And on top of that, it comes with this idea of a steep learning curve, right? As I will talk about later. But if you just focus on the aspect of learning the Einstein toolkit itself, then learning Illinois GRMHD, it's a lot and the physics going on behind it, it's just a lot to digest, right? So it discourages community adoption. It discourages, again, if you're newer to the game, it's very difficult to follow. The great analogy that was coined by, I think, Sam Cupp is this idea of like the tangled octopus, right? It's just everything becomes a mess and it's very difficult for you to detangle everything. And so what GRHayL tries to do is throw that away, right? And do something different and then basically, oh, okay, so I thought it was a different slide. So yeah, so our idea then is to start from Illinois GRMHD and then refactor it into smaller modules that are easy to understand. So GRHayL in particular is, well, I say the future there, but it's actually also the present, right? The current Illinois GRMHD already is written in terms of GRHayL functions. But it basically contains now, you know, better documentation. It's easier to learn. It's easier to contribute. And because GRHayL is a library that lives outside of the Einstein toolkit, it brings with it infrastructure agnosticism. And I'll give you an example of what I mean by that more as we go along. So basically, the idea is that we have this a better way for users to interact with the code and understand what the code is supposed to do. It's a modular code so that you can extend different parts of the code without having to worry about modifying everything at once or learning about the entire code at once. It has extensive documentation. Right now, the documentation lives in the form of wiki pages on our GitHub repository, but we're also moving towards a Doxygen website, which is on my plate to review for a while, and I haven't yet, but we're going to get to that. And infrastructure agnosticism. So these four core concepts basically form the pillars onto which GRHayL was developed. And the main goal there is just to create a better experience for both users and developers, right, in a way that is a little bit easier to deal with. You know, just listing things that I think might be obvious for everyone, right? But that new students, they need to learn, you know, physics, math, and computer science to just put it in a broad way of what we go through during our PhD, right? And it's also a known fact that typically computer science is the weakest links for many of the physics PhD students, right? And so what we propose to do, let me try to shrink this because I'm blocking my own view. Okay, I won't be able to do it. So our proposed solution is to have like small modular pieces, avoid using obscure language features. I know that's debatable, but our choice is to use just C. We don't use anything more complicated than that, and provide just extensive documentation on how the code works and what you can do to extend it. So yeah, so you know, through the small modular pieces, we can basically solve the problem of the code being completely tangled. And we created our self-contained modules called gems, right? You can think of a GRHayL as a cup, right? And there's a gem encrusted GRHayLs. through having no obscure language features, like I said, you just use C with minimum dependencies. Basically, the only external dependency we have is HDF5, and that's because we want to support equation of state tables, and they come in HDF5, so there was no way around that. And good extensive documentations, right? And like I said, we have the wiki pages, but we also plan to do Doxygen documentation that is a little bit more standard, I suppose. And so our goal is to take that tangled octopus that we had originally and just basically produce a nice cuttlefish that is completely detangled. And so in the spirit of that, right, the way that GRHayL works at a high level, but that it's very true to its nature, is that you start with your infrastructure, and in the case of many of the applications that we have, that infrastructure is Cactus or the Einstein toolkit. And we also have black holes at home or CarpetX, things that GRHayL have also been used for. And then you have GRHayL on the other side, right? So GRHayL as a library, you basically have our little gems, and our gems basically contain things that are typical in GRMHD. So you have something to compute the induction equations, a gem to compute fluxes and sources of the GRMHD equations, and have others that are just for the equation of state, and others that are just for neutrino physics or radiation. And then we can have stuff for other physics as well. So we still have room for expanding GRHayL. And then what GRHayL does is it provides, again, simple data structures in the form of C structs that you can use to essentially pack your data from your infrastructure to GRHayL, and then GRHayL will provide this back, allowing you to unpack the result of whatever calculation it does. And in doing so, right, in the spirit of the cuttlefish, basically this provides the connection that is needed to talk to GRHayL. And one of the nice things that we have done with GRHayL is that you can use GRHayL as a whole, as I'm showing here. But if you were to break off one or more of these connections, you can still use GRHayL. You do not need to use all of GRHayL to use GRHayL. So in principle, if you wanted to use just the equation of state module that GRHayL provides, you can do that. Provided if you don't want to use well, probably that was the worst example that I could have picked. But if you want to use any of the other ones, then you can use any of the other ones, provided that you give us some basic information about how to use the equation of state infrastructure or support in your infrastructure, basically. But basically everything in GRHayL is replaceable. You don't have to use all of it. You can pick and choose whatever you want. And so GRHayL went through a very rigorous process of validation to make sure that it actually agreed with Illinois GRMHD. And this process is kind of, well, it's probably easy enough to understand, I hope. So the idea is that we start with a random initial data, or some type of initial data for a problem, and then we pass it through GRHayL, right? So let's say we want to test if our conoprim is working. So we generate a set of initial data and pass that through the GRHayL conoprim, and we see what the output is, and we store that. And then we hijacked Illinois GRMHD from the Einstein toolkit. So we modified in a branch, we modified Illinois GRMHD so that we can read in that same initial data inside Illinois GRMHD and run it to conoprim, generate the output in the same format that the GRHayL format is, and then kill the run, right? So that we can get output from IGM, from Illinois GRMHD. And then we do that again, but this time we perturb the initial data at round-off level, and then we pass it through Illinois GRMHD, right? So now we have three types of output. We have GRHayL output, then we have Illinois GRMHD, and we have Illinois GRMHD with the initial data that went in perturbed at round-off level. So by looking at the two outputs from Illinois GRMHD, we basically create a band to which we deem the results to be acceptable, right? If the error is within that band, then the error is small enough for our test to pass. And then we compare the GRHayL output against that. So it's not every function go through this process, especially like if you have smaller functions that you can have an analytic result that you know what should come out of it. You can just run that through. But we have these bigger unit tests that run like when I say conservative to primitive in Illinois GRMHD, it's not just calling a single function. We impose physical bounds on conservative variables. We impose physical bounds on the primitives that come out. And so all of that is tested as a whole as well. So it's a very comprehensive code validation infrastructure. And in particular, GRHayL GRHayL has a continuous integration system based on GitHub Actions. It runs every time we push something to the repo, and it runs on multiple operating systems with multiple compiler combinations. We use that to validate the outputs against the trusted results. And pretty much every core function in GRHayL has individual unit tests. And as of this week, basically our unit tests are covering 93% of the library. And it's basically passing on everything that we're trying. So it's we're pretty proud of how far we've been able to validate everything. So this means we have to create tests that even probe like edge cases so that we can probe as many of the if statements that we have to make sure we're within correctness as possible. Okay, so now I'm going to talk about what we call the GRHayL implementations. So GRHayL, as I mentioned, is a library. It lives outside of the Einstein toolkit. It lives outside of any infrastructure. That means that every GRHayL function is basically, you can think of it as a pointwise function, right? It's a function that computes things at a single point in your grid, but it knows nothing about the grid. It knows nothing about the coordinate system. It's just a pointwise thing, right? So most of the functions are completely oblivious to the fact that your code might be doing, unigrid, AMR, grid patches, and whatever, right? The functions really do not care about any of that. And in doing so, this makes them very, very GPU friendly, right? That means that you can think of these functions as like a pretty much a replacement for any type of, like if you know CUDA programming, like a device type of function where you can just call that in by the GPU with no problems at all. Right? We don't do any memory allocations or deallocations. Everything is super simple. And so even though our GRHayL doesn't fully support GPU yet, we do not see any issues in adding that support. And in fact, we have plans for that. So let me see this. Yeah, so the implementations are where the connectivity comes from, right? So it's through the it's only in the implementations themselves that you're going to find loops, and you're going to find grid function access and function scheduling and things like that, or memory management, MPI, OpenMP, right? All of this is outside of GRHayL. GRHayL does not handle any of this, and it's up to your infrastructure to handle these. Oh, and there's I/O as well. Like GRHayL does some simple I/O for just erroring things, but you will not checkpoint anything for you and things like that. So in doing so, we really extracted all of the complicated parts of GRMHD code into an easy-to-use library. But the computer science difficulties that come with all of these things are left to the developer of the infrastructure, and it allows new users to focus only on the physics part of the code and not on any of these complications. So I think now I have, oh, not yet. So in doing so, right, what are the things that we reaped from doing this? Well, there are two main efficiency boosts that we have, and the first one I'm gonna compare against Illinois GRMHD, right? So we went full circle with GRHayL. We started with Illinois GRMHD. We ported all the algorithms into an infrastructure-agnostic library, and then we used that library to rewrite Illinois GRMHD. Right, and so now we have a new version of Illinois GRMHD that basically is from GRHayL, right? And if you use this with what we call the hybrid equation of state, that is not using the finite temperature equation of state tables, then we see a 30% speed up in just the way the GRMHD code is doing things in the Einstein toolkit, right? So the new version has a significant speed up, and that was just removing a lot of technical debt from Illinois GRMHD that I added actually my technical debt comes more on the tabulated EOS side, but there were a lot of technical debt that we cleaned up, and the scheduling was done a little bit differently as well. But one of the things that we're really proud of, and I'll explain the number, is that we see a 90% reduction in the development of new GRMHD codes, right? and in the time that it takes to develop these codes. And the way we measure this, right, is that in a conservative way of saying things, it will probably take 1 to 2 years to fully develop the GRMHD code from scratch, for example, for the Einstein toolkit, right? If you want it to be fully validated, go through all of the tests that we normally do, and make sure that everything's working with confidence. That's a reasonable timeline for a student to implement something like this. But once GRHayL was ready, one of the PhD students in our group, Terence Pierre-Jacques, actually created a new GRHD code inside the Black Holes at Home infrastructure in just shy of 2 months, right? Because it was able to do GRHayL. Granted, it does not have magnetic fields, but it is in curvilinear coordinates, right? The code's called Groovy. So it's, in many ways, there are complications that are out of the scope of the Einstein toolkit, but we don't do yet multi-patch AMR stuff. But, in the future, we're going to do that as well, multi-patch in curvilinear coordinates. So yeah, so that's the way we are measuring here the 90% reduction in code implementation time. So let me just make sure this is the slide. Yes. So I want to give you an example of why it is that why we think that it takes far less time to implement these things in new infrastructures, right? And the way I'm going to do it is by showing what the code looks like in Illinois GRMHD, and then what it looks like in Groovy, this code that is part of Black Holes at Home, right? So I don't know if everyone here is familiar with the Einstein toolkit, but this is just a very general thing that you see in every Thorn that you ever write or ever have to read, right? We start by having a bunch of includes, and GRHayL's implementation as a library within the toolkit is called GRHayL_lib. So it provides this GRHayL_lib header.GRHayLlib.h. And so in one of the functions in Illinois GRMHD, we have that, right? We include that. Then you have the definition of the function inside the Einstein toolkit. So it's this, this is the hybrid version of the conservative to prim function that also has entropy evolution, and it takes the typical CCTK arguments that you will see in the Einstein toolkit. And then, so we're going to do conservative to primitives, right? So then you're going to have a loop. This is the typical loop again. I know there's a shorter way of doing this loop using a macro, but we didn't do it with the macro here. So we're just looping over the interior, and we're going to be accessing grid functions to be able to do that. And then we're going to read in, so we read in from the grid functions all the conservative variables, right? So we have a GRHayL struct called this GHayL conservative quantities. And we're basically reading in things from the grid functions, and these were defined by Illinois GRMHD. I'm not giving you all the details about where these come from, but trust me that those exist. And then we're reading it into the GRHayL struct. And then once we read it into the GRHayL struct, we call the conoprim function inside of GRHayL, right? And again, I'm omitting parts of the code that do things that are less relevant for this exposition. But basically, once you call this function, inside this prims struct will be the answer of conoprim. And then you can just do a similar version of this, but unpacking, from reading from this into the grid functions instead. And now I'm going to change from this slide to the Black Holes at Home version of this same function, right? And you can see, like, if I go back and forth, right, you can really do like a diff between the two files, and it's very, very easy to see where things are different, right? So in particular, for example, this version, so because GRHayL is not code generated for the most part of it, we have this general version called conoprim multi-method that will detect whether or not, which type of equation of state you are using, and it will do everything for you. It will do most of the if statements at initialization. It won't keep doing the if statements over and over. But most of that in the toolkit will happen at initialization. But Groovy, on the other hand, is a code that is code generated by NeRPy. And so because this is the tabulated equation of state version of Groovy, there's no reason to add that other layer of if statements. Groovy can already call the direct tabulated multi-method here. That's why there's a slightly different name for conoprim there. But again, you can see how pretty much they are identical. Granted, Black Holes at Home has a lot of resemblance with the Einstein toolkit in some aspects, but yeah. So our current implementation, so again, when I say implementations, think of full codes that use GRHayL, but to do other purposes, right? Include Illinois GRMHD with support for both Carpet and some support for Carpet X. I think Sam did have a Illinois GRMHD X at some point. I don't know how much that is actually working or not. Maybe I shouldn't have put that. Then we have a version of Illinois GRMHD, which removes the M, so GRHayL HD. So that's again part of the Einstein toolkit through Carpet and Carpet X. And there's this NeRPy version with Groovy. Then we have NeRPy leakage ET. NeRPy leakage ET leverages the neutrino physics part of one of the GRHayL gems to produce a module in the Einstein, a thorn in the Einstein toolkit for neutrino leakage. Then we have Tavala, which is a TOV initial data solver for the Einstein toolkit in Carpet as well. We have Groovy with a misspelled R there. Sorry, it should be capital R, which is a GRHD in the Black Holes at Home infrastructure. And we have some now, especially some support for, we're replacing some of the GRHD infrastructure in the Manga code, which is this unstructured mesh GRHD code that we work with. And for future infrastructures, for planes that we have, worked with some of the folks, and they have shown interest in using GRHayL, we have both GRChumbo and DendroGR. And your infrastructure could be here too, if you want it. Just let us know. And then, what the future holds for this is we're still having some validations that we need to do, and we want to support Carpet X a little bit more fully than we do now. And then we want to, truly make the jump between, yes, we are GPU friendly, and most of our kernels should work with the GPU out of the box, but we need to do that and actually make it support GPUs, right? We need to add GPU supports to GRHayL. And then we also want to do radiation transport a little bit more, in a little bit more, let's say, advanced than what we do now, right? So in particular, we want to have a neutrino M1 gem inside of GRHayL, and David Boyer is working on that right now, and so is Johnny Tsao, which is providing a much appreciated contribution that is not coming from our group. And then two other additions that we plan to hope building on that is a photon leakage code, which will likely borrow a lot from what the RIT folks are doing, or from some of the new codes that are being discussed in this school. Oh, and that's it. Yeah, I thought I had one more. Okay. So yeah, I knew I wasn't going to be able to talk for 1 hour about this, so at least I kept it a little bit shorter. But I'd be happy to take questions. Yeah. Yes. You can just set the magnetic field to 0 and have Yeah, there are a lot of complications added by having that magnetic field in there, and like in particular, I agree. If you have, like, that's one of the tests that we do, right? Is compare the GRHayL HDs. If you have a problem with the magnetic field code, the great way to do it is to set the magnetic field to 0 there. But in particular, like where you're trying to do the variable reconstruction, it adds a lot of complication by having the magnetic fields in there. So it is mostly a performance thing, but yeah. Sorry, what? Oh, yeah, the question was if the reason for having a pure hydro code versus just setting the magnetic fields to 0 in the GRMHD code was just for performance. And the answer was yes. Yeah. Yes.
Having those two versions, one with the M and out, does that create any maintenance issues, or is there some automatic way of factoring it out? Or?
Yes.
I would think that that's the kind of thing where you say, oh, I want to fix this, but then I have to fix this code too.
Yes, it creates that problem. Yeah, so the question is, does that create a maintenance issue? Because now you have two thorns to maintain, right, instead. And yes, it does create that, and we have to propagate things. Yes.
Inside grid.
Yes, yes. All of the maintainability comes from the connectivity, right? It's just like if you messed up one loop and you realize that both thorns had that loop messed up, you're going to have to fix it twice. It's not, yeah. But,
I
yeah.
just wondered if you had some fancy automatic.
In principle, I guess we could, but
That is almost definitely going to be just swapping something out within the library with something's functionally equivalent, but GPU support.
yeah.
In some ways, it feels like a thing where you'd want to use an if that, but on the other hand, it might be that you litter your code with if that. So there's this trade-off.
Yeah.
Any more questions?
Yes.
So if we're just using GRHayL as the library part, and since it's not like it wouldn't know the grid structure, so for things like the shell capturing, things that deal with grid, you have to implement it after.
So yeah, so that's yes. So if we're dealing with things that are like agnostic for the grid, then like how do we do shock capturing? Basically, that's the idea. So the shock capturing part, so the reconstruction is the only part that GRAIL doesn't really act pointwise. It actually needs you to pass a little stencil of points across the face that you want to do the reconstruction. Yeah. So that's the only one that is not truly. So for example, in Groovy, the way that we do that is first we convert quantities from the reference metric basis, whatever there is, like spherical coordinates, to Cartesian coordinates, and then we use GRAIL, and then we convert back. It's something like that. Because the way we have the reconstruction, there are some pressure gradients that really want to be done in X, Y, or Z or something. So yeah, but a lot of the things that we have are completely agnostic to that, and you don't have to modify anything. Like, yeah.
And then thank you to all of our speakers today. And here, let me just take that real quick so I can. We will be back here tomorrow at 9 a.m., I think. Do you want to remind people about the TAC thing or anything?
So I will bring up the announcement again tomorrow. So stay tuned, I guess.